Okay, let's get started. I guess most folks can hear me. So, okay, so this is today's plan. So from the last week, I started talking about CUDA sublimation. So the last week, I started talking about the CUDA. So in this week, I continue discussing CUDA. And you hopefully have some time to work on this CUDA exercise. And the other notebook I just gave for the purpose of visualizing how GPUs actually work. And actually, there is a small correction on the notebook, so I come to this later when you have a chance to work on that. And the other correction about this exercise was, yeah, I hope many of you have somehow figured that out. But so obviously, so this square root cannot be taken for all xy's in this region. So just consider you actually integrating the part of the unit disk. So all the xy that satisfies inside the square root is positive. So, or alternatively, so alternative way to put it is simply that you simply consider this integrand 0 anywhere outside the unit disk. So either way, just ignore when you when the what comes inside the square root becomes negative. So this is how you work around. So of course it's my bad, but and just hoping so many of you have figured that out. So this is my bad. Here's how you avoid it. So okay, let's get started with CUDA again. So I got a question about this open key thing, but I'll get to that later. So not now. So let me start talking about CUDA. So I guess this is where we left off. So okay, so I talked about, okay, so here's how you launch a CUDA flex with this somewhat awkward syntax. And you had a chance to do something using CUDA. So so let's continue discussing CUDA. So here are some small things about CUDA programming. There are some keywords you need to remember. Those keywords are attached to just in front of function, just like where you have actually seen before here. So there are three important keywords you have to remember just to attach in front of functions. One is global, another is device and host. So basically, device and host are somewhat obvious. So device basically says this function should be compiled for GPU or device. And host says, okay, this function should be compiled for the host CPU. So global is somewhat different. So it's basically device. It's basically compiled for GPUs, but it can be called from a CPU code. So this device code can be called only from GPU. but this global is a kind of entry point from CPU to GPU. So this is a keyword you have to attach to the function you want to call from host, from CPU to GPU. And another restriction is this global function cannot return a value. So it must be a void function, just like, okay, I forgot to say void here, but it has to be void function. It cannot return a value. And this is sort of annoying and inconvenient. And one thing you might want to know is you can actually have both host and device in front of a single function. The end result is that the compiler generates both versions, one for GPU and the other for CPU. So one thing you might want to remember. And another thing that kind of details, but sometimes necessary and useful is these predefined macros, NVCC and CUDA arc. So this NVCC predefined macro is defined when something, so when your source code is compiled by this NVCC compiler. So this is sometimes convenient and necessary when you like to have a single source code that is sometimes compiled using NVCC and sometimes compiled by other ordinary host compilers like GCC or CLAN or whatever. So this is what you typically do to have a single source code with two different implementations for GPU and CPU. And the other similar but slightly different macro is this CUDA arc. So this is a macro defined when some piece of code or function is compiled for device. So this is convenient when you have a function having both device and host keyword, saying, I want this function to be compiled both for GPU and CPU, but have different implementations depending on whether it runs on GPU or CPU. So those two things are very similar but different. So NVCC is defined everywhere when something is compiled using NVCC. But this CUDA arc is defined only when a function is compiled for GPU. So these two things are at times very useful to maintain a single source code for GPU and CPU. Okay, the next section, somewhat more substantial section about threads and thread blocks. So this is just a recap of what are threads and thread blocks in CUDA programming. So recall that a kernel, a function with this global keyword attached to it, specify the action of a CUDA thread, right? And you run this function using the awkward syntax I just mentioned the last week. Triple smaller than and triple greater than. And when you launch a kernel, just remember you specify the number of thread blocks and the number, the number of thread blocks and the number of threads in a single thread block. So rather than just saying you want to launch 1,000 CUDA threads, you say, okay, you want to launch, let's say, 20 thread blocks, each having, let's say, 64 CUDA threads. So this is the CUDA way of launching many threads. So the effect is to simply create NB multiplied by BS number of threads. So it can be illustrated like this. So each white box is a thread block, and each yellow guy is a CUDA thread, a single CUDA thread. So you have here a single CUDA, single thread block having something like in this particular figure, something like 4 threads. Typically, you have many more, and you have so many thread blocks. And I explained how you can know the rank of the thread within a single thread block and the rank of your thread block in the entire grid. So just like thread index or block index, each assigning a unique number to each thread block and each thread in a single block. So you might naturally wonder why you need to say 2 separate numbers rather than, okay, in total, I like to get 1,000 threads, for example. So there are several reasons for that. So a few reasons I'm going to get into in the next couple of slides is something that is semantically important. So something that affects the correctness of your program. So there are other reasons related to performance, how you get performance. But in the following couple of slides, I will not be talking about the performance. So the only thing that matters for correctness, how you get your program right. Okay, so but still, it is useful, instructive to talk a little bit about how GPU work when it is given a number of thread blocks, each having many threads inside. So this is illustrating what happens when you launch a kernel using a notation like this. So you launch NB number of thread blocks, each having BS number of CUDA threads. And this is an illustration of a single GPU device. And each green box represents a streaming multiprocessor. So just like a physical core of a CPU. And actually, each streaming multiprocessor is able to schedule multiple thread blocks simultaneously. But the point here is that GPU dispatches threads, one thread block at a time. So it never happens that, for example, the GPU executes this thread on this streaming multiprocessor while execute this guy on another streaming multiprocessor. So thread blocks, a thread block is the unit of scheduling from the perspective of GPU hardware. So what GPU is doing is essentially fetch a thread block at a time and dispatch sends it to whichever streaming multiprocessor that happens to be available at that time. Okay, so just consider thread block is sort of the unit of execution from the perspective of GPU hardware. So I'll come to this topic later, but just for now, just remember that it is not that each streaming multiprocessor is able to execute only one thread block at a time. It is able to execute multiple thread blocks at the same time. But nevertheless, it never happens that a part of thread block is executed on streaming multiprocessor 0, and the other part of the same thread block is executed on another streaming multiprocessor. It never happens. So actually, there are two ways in which this boundary between thread blocks are visible from the programmer's perspective, except for performance. So the thread block boundaries are semantically visible. They affect the correctness of the program. So one is that CUDA API exposes something they call shared memory. So this is clearly a misnomer, but the shared memory is a small cache-like fast memory that is only shared within a single thread block. So threads within a single thread block, like these guys, shares a part of the shared memory. So they can communicate through shared memory. On the other hand, the other sort of default memory is something called global memory. And it can be shared among everybody. So every thread in the entire grid. But shared memory is shared only within a single thread block. So this is one way this thread block boundary is important from the programmer's perspective. So unless you put two threads in the same thread block, they cannot share data through shared memory. So they can still share data through global memory, but it is slow compared to shared memory. So the other way is that there's one synchronization primitive called, again, this awkward name, sync thread. That is usable only to synchronize threads within a single thread block. Okay, so when each thread in a thread block calls this sync thread function, they synchronize only within a single thread block. So they cannot synchronize between different thread blocks. So actually, unless you rely on one of these primitives, the boundary between thread blocks are largely invisible from the programmer's perspective. So you can consider just that they are just a bunch of threads without worrying too much about where's the boundary between thread blocks. But these two tools are actually shared memory and sync threads are actually important for performance reasons. And these are two ways the boundary becomes visible from the programmer's perspective. Okay, so there any questions so far? Okay. So yeah, this is so one way I address the earlier question, why you have to say two numbers. So I come to this later again for when I talk about performance. But for now, these are the two main reasons. So then the next thing you need to master is how host CPU and device can communicate. So just remember that GPU is a separate device, separate from the host CPU. And they do not share memory. So host memory and device memory are separate. So you just imagine there's some memory around here and another memory just next to the CPU. The device cannot access data on the host and vice versa. So CPU cannot directly access data on the GPU memory. At least not directly. Well, actually, this situation is actually changing. So it is very natural that all these GPU vendors are trying to make GPUs more convenient. So actually, the shared memory between GPU and CPU are just now emerging. But for the time being, you still have to master how you explicitly move things between CPU and GPU. So it's still worthwhile to learn how you do it. So what this means from the programmer's perspective is that the code that looks as simple as this doesn't work. So you have an array of double, and you are passing the array A, or more precisely, the address of the array, the pointer to the array, to GPU by doing this. And the GPU takes a pointer as an argument and accesses it. So it's not going to work. What actually happens is that this gets segmentation fault or some similar memory access violation on the GPU side. So you have to do something about it. Okay, this is just an illustration. Don't forget. So here comes two more things you have to master before writing any useful program using GPU. They are something called CUDA-malloc and CUDA-memcopy. So first, you need to allocate data on device. This can be done by calling CUDA-malloc, just as you normally call malloc functions or new function. So the defect, you get some amount of memory on the GPU memory, and the host CPU gets the pointer to this GPU memory back. So let's call it a def. And the other thing is, so just allocating memory on the GPU isn't enough to do anything useful. So you need to somehow fill this memory with the data you want to pass to the GPU. So there is another function called CUDA-memcopy. So this is a generic function with which you can move data between the host and the device in both directions. So host to GPU or GPU to the host. So by setting the contents of this ADEF chunk of memory by calling CUDA-memcopy, you can pass the pointer to this ADEF to the device code. So one thing I have to note here is that you have to call both CUDA-malloc and CUDA-memcopy on the host, not the GPU, not the device. So you cannot actually call dynamic memory allocation in the device code. So the capability of GPU is quite limited when it comes to dynamic memory allocation. So you have to do all these memory allocation things basically on the host CPU. So here's some typical steps to send data to the device. So to move things from the CPU to the device. So normally you actually have a copy of the data the GPU is going to work on the host side too. So it depends on where the data is actually coming from. But typically the data is generated by the host or it's read from some sort of file. Either way, the first one that generates data is typically CPU. So you typically have so something called the original data on the CPU anyways, and you have the data that corresponds to this original data on the GPU side. And you call CUDA-malloc with intention that ADEF holds a copy of this A on the GPU. And the host works on the host data. So it prepares whatever data you want to pass to the GPU by assigning elements. And copy the data to the device by calling CUDA-memcopy. So this copies the size bytes of data from A to ADEF. This flag specifies you want to move data from host to device. And finally, you can pass the device pointer to the kernel. So you shouldn't pass this A, so you instead should pass this ADEF. So as such, So in CUDA programming, it is often a good idea to have a structure encapsulating both pointers. So one structure from outside. So it just looks like a single ordinary data structure from the outside. But it internally has two pointers, one pointing to CPU memory, the other pointing to GPU memory, having the identical contents. So you somehow maintain the consistency between these two data structures. This is what you typically do in CUDA program. So here are some typical steps you go through to get some results back from GPU to CPU. So just like before, you allocate GPU shadow copy of the original CPU data, and pass the device pointer to the kernel. So unfortunately, like I said earlier, all the kernel functions must be void. So you cannot simply return any value. So the only way you can effectively return some value from the CPU, from GPU to CPU is you pass a pointer to which GPU is supposed to write the result into as a function argument. And GPU does some calculation and fill this RDEF data with whichever result you want to get. And after this kernel is launched, you copy the data to the host, again by calling CUDA memcopy, but this time with the opposite flag. So memcopy device to host. So if you master these two things, so this is how you can pass data from CPU to GPU. And here's how you can get the result back from GPU to CPU. Pretty much, they are pretty much all you need to master. So just one note about alternative way of doing it, something called the unified memory. So recent GPU, NVIDIA GPU supports something called the unified memory that basically eliminates the need for explicitly moving data between GPU and host. So it's just like a shared memory between GPU and CPU. And actually, this is an emerging topic. And so recent GPUs, so especially combination of NVIDIA GPU and IBM Power CPU, or combination of AMD GPU and AMD CPU. So they are supporting this unified memory by hardware. Unfortunately, it is not supported on the platform combining Intel CPU and NVIDIA GPU. But actually, something you might actually call pseudo unified memory or software emulated unified memory is more widely available, including Intel plus NVIDIA combination. So in terms of API, you can just use it, but it's actually slow. So you cannot expect too much performance out of it. But the thing is, just replace CUDA malloc with CUDA malloc managed. So it allocates GPU device, but somehow accessible both from CPU and GPU, and data is somehow kept coherent. But again, like I said, and do not expect excellent performance, at least for now, on Intel plus NVIDIA platform. But with that said, this is how you can send data back and forth between CPU and GPU. So this is steps to send data from CPU to the device using unified memory. So the only difference is that you call CUDA malloc managed instead of CUDA malloc. And that's basically it. So you don't have to call CUDA mem copy. And you can maintain only a single pointer, which is very convenient from the programmer's perspective. And here again, so here's how you can retrieve the result with a unified memory. Again, you just allocate memory by CUDA malloc managed, and that's pretty much it. So just use it when you find it convenient, and the performance implication is not that severe. So the last topic before you have some time to work on the notebook again is the data sharing among threads in the device. So I just talked about data sharing between CPU and GPU, which is, well, at best awkward. But this is how data is viewed among threads in the device, the same device. So the basics is that basically the CUDA threads, the only memory region CUDA threads are able to access is memory allocated by CUDA malloc or CUDA malloc managed. And shared memory, I likely talked about before. And the basics is that this memory region allocated by CUDA malloc or CUDA malloc management, CUDA malloc managed, are shared among all threads. So you just consider this is a big shared memory among all threads in the GPU. And this memory is called global memory. So this is a global memory that is accessible by everybody in this entire grid. And here's another thing I likely mentioned before, something called shared memory. So in terms of the how hardware is structured, it is just a small on-chip memory that is attached to each streaming multiprocessor. So each streaming multiprocessor has a small on-chip memory that is accessible only within the same shared memory, streaming multiprocessor. So how this can be visible from the programmer's perspective is that so only thread within a single thread block can share the data in shared memory, right? So it is guaranteed that threads in the same thread block are never executed on different streaming multiprocessor. So it is guaranteed. Therefore, it is guaranteed that these threads within a single thread block can share data on shared memory. So basically, you have to remember only these two things. So one is global memory that is shared among everybody. And the other is shared memory that is shared only among threads within a single thread block. So actually, there are some other types of memory if you look into CUDA programming manual, but I don't get into them. So they are not as important as these two things. So by the way, this shared memory is, in my opinion, it is a complete misnomer. Shared memory should be a name of something that is shared. So, but in CUDA terminology, shared memory is a memory shared only among threads within a single thread block. And global memory is true shared memory in a sense. So it's quite confusing, but this is what they are in CUDA terminology. So because data is shared, at least on global memory, so basically the programming model is quite similar to what you have in OpenMP. So in OpenMP2, so you have two threads. Basically, you share all the data by default, unless you specify otherwise, right? So the same problem happens, which is a race condition. So when two or more concurrent threads access the same location, and one of them is writing to it, then yeah, the programs almost always are broken. So the programs behave somewhat non-deterministically, which almost always means that program is not what you intended. So just as an example, I briefly talked about this example in the last week too. So this is a example code doing sparse matrix vector multiplication using COO format, coordinate list format. So when you run this code, then it might happen that two different threads are trying to write to the same location, the same element of I. So this code is not going to work. Actually, how you fix this? So how to work around this problem is conceptually very similar to what you had in OpenMP. So just remember what you had in OpenMP. So one is something called critical. That makes sure that this piece of code does not run simultaneously, even if they are executed by multiple threads. Another one is something called atomic. So with which you can do, for example, read this memory, add something, and write the new value immediately back into the same location. And the final solution was something called reduction, right? So conceptually, they are very similar. So in CUDA, you have atomic accumulations. So more specifically, a function called atomic add, and some other similar functions. And actually, CUDA does not have something analogous to a Pragma OMP critical. So it has no way of, so it has no generic way of making arbitrary piece of statement appear atomic. So it doesn't have something similar to mutual exclusion. So actually, I didn't talk about it in the OpenMP context, but CUDA has something called the barrier synchronization. You can build reduction on top of this barrier synchronization. So it actually has a reduction as a primitive, so that you can just call it. But it somehow only works within a single thread block. I don't know there's any fundamental reason why this is the case. So you can build a reduction across many thread blocks on top of barrier synchronization across thread blocks. So I don't understand this omission. I don't know if this omission is intentional or not, but this is where they stand somehow. Okay, so this is what atomic accumulations actually look like. So the situation I'm talking about here is, okay, so you have array all initialized to 1, and you are calling a CUDA kernel that whose intention is to get the summation of all the elements of this array A. And the result is supposed to come at the first element of this array. So the goal here is to guarantee that it always prints the sum of all elements in the array correctly. So in this particular case, it should print exactly NB multiplied by BS because all elements are 1 and you range NB multiplied by BS number of threads. So this is the race-prone version, which does not work always. So what it is doing is simply the thread I takes the ith element of A and accumulate it into A0. So obviously there is a race condition on this element A0. It otherwise works, but because of the presence of this race condition, it is not going to work. So the way you can fix it is very simple. So you simply call this atomic add instead of straightforwardly doing something like this. So this atomic add guarantees that this addition becomes atomic. So this is quite similar to what you have in OMP atomic, right? So this is in many cases useful. And you can make it, make our example coordinate this version of sparse matrix vector multiply just by replacing this yi plus equal aij multiplied by xj by atomic add. Right? So another thing, various synchronization. So yeah, because I didn't talk about it in the OpenMP context. So what is a various synchronization? So various synchronization is a synchronization mechanism of primitive to guarantee that all threads reach the point. And before all threads reach a certain point, nobody goes ahead. So this is what the various synchronization guarantees. So it can be illustrated just like this. So all these threads at one point are called barrier function call. Then no threads no threads go ahead until everybody calls this barrier function. So the original CUDA in the very early version used to support this single function call, something called __ sync threads. So this is the barrier synchronization mechanism within a single thread block. This used to be all you have in CUDA programming. The situation is now somewhat better when they introduce something called cooperative groups. So I'm talking about this cooperative groups because it is, well, in terms of the functions it provides, simply superior to what a sync thread provides. So so basically, when you use this cooperative groups I will be talking about, and then actually you need to call the kernel differently. So conceptually, it is almost doing exactly the same thing, but instead of using this convenient awkward syntax like F A0 A1 blah blah blah, you instead need to call this function, so CUDA launch cooperative kernel. But conceptually, you are doing exactly the same thing. So you are passing a function f, specify the number of thread blocks and the size of each thread block, and you are passing the same argument, but using array of arguments instead of just listing all the elements. So conceptually, they are the same thing, but the subtle difference is that there are some further restriction about the number you can give to these two arguments. So number of blocks and the size of each thread block. But otherwise, they are conceptually very same thing. And before doing something like this, you need to include this header file cooperative groups.h and just set up the namespace for the convenience. And inside your kernel, so GPU code, you can do something like this. CZ this grid. So you get some data structure representing the entire grid, so all threads, or CZ this thread block to get data structure representing the thread block you are in. Either way, after you get this data structure representing the entire grid or the thread block you are in, you call this g.sync to establish the barrier synchronization among all threads in this thread group G. So either everybody in the grid or all threads in the thread block you are in. So this is simply somewhat more general than the very awkward sync thread primitive that is able to only synchronize threads among a single thread block. And also another thing is, so this group interface actually provides a cleaner way to know thread ID and number of threads. So rather than the awkward variable names I talked about the last week. So grid team, block index, block team, and thread index. You can simply call g.thread rank or g.size, which is much cleaner in my opinion. And you can actually build reduction on top of barrier synchronization. So this is somewhat advanced topic, but I am talking about this because reduction is very important. And CUDA does not have a built-in reduction among all threads in the entire grid. But it has a barrier among all threads within in the entire grid. So it is very useful to build reduction on top of barrier. So this is how you can do this. So just consider that you are trying to calculate the sum of all these numbers in the array. And you just launch as many threads as the number of elements of the array. And in the first step, so basically you do this using a series of barrier synchronizations. So you have a barrier here, you have another barrier here, you have another barrier here. And before the first barrier, what you do is, okay, so this thread takes this element and takes the summation of the two and put the summation into its own element. And similarly, this guy takes the sum of this element, its own element, and this element, and put the result into its own element. Right? So this way, all the threads in the first half of the array are taking the sum of two elements, resulting in something like this. The first half of the array becomes 2 in this case, right? And you take another barrier here. So what is the purpose of the barrier? So the purpose of this barrier here is that to make sure before any thread goes ahead, all threads complete this 1 + 1 = 2 calculation. So this is the reason why you need a barrier here. So you just keep doing until you get the total of the elements. So in terms of the code, it looks like this. So each time actually you halve the number of elements. So by something like this. So you approximately halves the number of elements. And in the next iteration, the number of them becomes the half of the original one. And each time, if so, I plus h refers to, for example, from this guy's perspective, I plus h is here, and it is still within the bound of the array. It gets this element and accumulated into its own element. So everybody keeps doing it until you get the final single element. So this is how you can build reduction on top of barrier. So if you have this at in your disposal, then CUDA programming looks very much like OpenMP, except that you have so much more thread than you typically have in OpenMP. Conceptually, they are very similar. And finally, about shared memory. So I talked about shared memory in passing the few times. So what it looks like from the programmer's point of view. So actually, from the programmer's point of view, it is another parameter you can specify when you launch your kernel. So rather than just specifying the number of blocks and the block size, you specify as a third parameter the size of shared memory you want to give to each thread block. So how you access this allocated shared memory from within CUDA threads, I'll come to this shortly. But for now, this is the way you can specify the size of shared memory you want to give to each thread block. And like I said several times already, so from the CUDA program's perspective, it is a memory only shared within a thread block. So only shared among threads within a single thread block. And it is only active during the thread block's lifetime. So it is actually another difference between shared memory and global memory. So whatever you have written to global memory stays there even after the kernel is finished. But shared memory is active in the sense that you can meaningfully access it to retrieve whatever value you have written to, only during the kernel's lifetime. And again, okay, so I have already complained about this. So shared memory, the terminology is a complete misnomer, in my opinion, but I have already complained about it. And also, yeah, like I said, so physically, so in terms of the physical implementation, it is a small cache-like memory that is faster than global memory. And as such, so it is very natural that each streaming multiprocessor has a fixed amount of shared memory. So you cannot have infinite amount of shared memory. And it is actually much smaller than the global memory. So typically, global memory is something like 40 gigabytes or 80 gigabytes, whereas shared memory is actually as small as 100 kilobytes or 64 kilobytes. So it slightly depends on the generation of the GPUs. And I forgot to write about the latest model, Ampere, which you are going to use. So it has something like 160 kilobytes, so slightly larger than earlier generation, but still it's very small compared to the global memory. And so the obvious limitation that stems from this the limited size of the shared memory is that Did I get it right? S multiplied by BS. So S is the size of the shared memory to each thread block. So if you multiply it by block size, what I'm doing? Yeah, I think that I don't know. Let me think about it again. So I'll come to that later when I figure that out. So maybe I'm making a slip here. So I'll come to this later. And so this is another thing I have to explain before you can actually use shared memory. So this is how it looks like from the perspective of GPU threads, so CUDA threads. So this is how you can access shared memory from CUDA thread. So like I said, you specify the size of shared memory given to each thread block by the third parameter when you launch a kernel. And this allocated memory can be accessed from within a kernel code by this keyword, mysterious keyword called a share. So basically you declare an array of arbitrary type, like int an or whatever, char bm or whatever, and you put this shared keyword in front of the array. Then this array is allocated on shared memory. So this is how you access shared memory from CUDA threads. And actually, you do not have to make the size of shared memory compile time constant. So you can do something like this. So you just say extend shared char whatever, and you don't specify the number of elements of this array. Then this whatever becomes the beginning address of the shared memory. So you can actually allocate whatever data structure you want to allocate to shared memory based on this pointer, based on this address. So you typically do something like this. For example, if you want to allocate some number of integer elements, so you want to have an array of integers, you do something like this. So you simply assign whatever to a pointer pointing to the integer, and you simply assign a plus m, this address to the next array you want to allocate. So you can do something like this, very low level address manipulation. But this is how you manage shared memory within CUDA programs. And your shared memory is useful because it's faster. It's faster than global memory. So I come to this later in later weeks of this course. But so it's primarily a way to efficiently communicate among threads within a single thread block. But actually, GPU also nowadays has a hardware managed caches. So just like CPU caches. So how crucial is it for the performance down the road? It's changing over time. So in future, it may not be that important if GPUs are equipped with hardware managed caches. Okay, so I think with that, I basically explained all you need to master to write a correct CUDA programs. So performance is another thing, but as far as the correctness is concerned, this is pretty much all you need to master, at least as the basics. So I guess it's time to do some exercise, PD02 or whatever, depending on where you are. So let's have this exercise time until 6:10, so 90 minutes. And I got a question. So the first one is open. Okay, so the first one is somewhat specific to the open the exercise. So I come to this later. And the second one, again, it is about assignment one. Okay, so I answer to these questions later. So let's get started with the exercise for now. So exercise until 10. So I got a new question about how you're supposed to submit your assignment. So you're supposed to submit assignment both on Jupyter and ITCLMS. So it is actually clearly written in the ITCLMS instruction. So what you're supposed to do is do submit operation on Jupyter first, like just pressing this after you have done, and you're still supposed to write a short report. So it doesn't look like a report, but to the ITCLMS. The only thing you need to say in ITCLMS is essentially you are done. So you have just submitted the notebook to Jupyter environment. So the short answer is yes, you are supposed to do both. Okay, so let's get started again. So before we proceed, some questions I can answer now. So the first question is, so if you do not use reduction, and which means you either use OMP critical or OMP atomic, it gets actually uh, slower, so presumably slower than sequential code. Is that normal? The answer, yes. So basically, it is very common that I come to this point in later weeks when I dig into performance issues. But so generally speaking, when multiple threads are trying to access the same memory, then yeah, it is actually very costly. So a single memory access that was just accessed by another core is easily taking more than 100 cycles and sometimes 500 cycles, way more costly than ordinary calculation. So do not be surprised when it gets slower when you're using critical or atomic. So the other question, I don't think I can answer right away. So you don't see any difference in performance between different scheduling policies. So no matter how you use static or dynamic, the performance didn't change. Is it the way it's supposed to be? I don't know. I think I need to look into what you exactly did to answer this question. So it's basically not supposed to be the same across all the uh, different scheduling policies, generally speaking. Yeah, I think I answered this question. So the other question about the assignment was, so you see only one assignment in ITCLMS, only about PD01 OMP. So other notebooks are going to be another ITCLMS. So actually, I'm not trying to make every single Jupyter notebook assignment. So in many cases, I just give you assignment just for your own exercise and don't make it assignment. So specifically, the PD02 CUDA is not going to be another assignment. PD04 is not going to be another assignment. So I will announce it clearly in the ITCLMS when I make another assignment. And the last one, there seems something wrong in the code I gave. So yeah, obviously this is not something I'm aware of at this point. So I look into it later. So I cannot answer right away. Okay, so you think you have an answer to the scheduling policy. So let's get into it later anyway. So let me go ahead for now. All right. So the last topic in this slide deck is, well, so in terms of how you actually do CUDA programming, it is basically about how you choose a good block size. But in this opportunity, I'm going to talk a little bit about how GPU works and what is, generally speaking, a way to get a better performance. But primarily, the topic is, superficially, the topic is about, okay, so when you want to create, let's say, 1024 threads, what is the difference between, for example, creating 1024 thread blocks, each having only a single thread, and, for example, creating only a single block, having 1024. or somewhere between them, like creating 4 thread blocks, each having 256 threads. So you can have a variety of way to create the same number of threads, right? So superficially, it is about, yeah, what is the appropriate block size? So before getting into what is generally good for performance, there are some absolute constraints you need to always adhere. All the performance issues aside. So one absolute constraint is where the block size is at most 1024. So you cannot have a single thread block having 2048 threads, for example. And another constraint which I'll get to in the next slide is the usage of registers. So I come to this in a few slides. And the other performance consideration. So it is basically about how to utilize resources in streaming multiprocessor. So if you have only 2 huge threads in a single streaming multiprocessor, it may not be able to utilize all the resources it has. So there are some performance considerations when you choose appropriate block size. So when we talk about performance considerations, actually there are 2 things. One is how you maximize the utilization of a single streaming multiprocessor by having enough parallelism within a single streaming multiprocessor. The other is, of course, obviously, when you have, for example, 108 streaming multiprocessor, you want to use all of them to get more performance, right? So the other dimension is the parallelism across shared memory, streaming multiprocessor. So these things are generally what you need to consider when you choose the appropriate block size. So first about registers. So registers, so it is the most basic resources for any sort of processors, whether it's a CPU or GPU. So it is used for example, holding the values of variables, holding the value of intermediate results. So each CUDA thread obviously consumes some number of registers to hold its local or temporary variables, right? So you don't have to know the exact mechanism in which this number is determined, but this is primarily a compiler job. So when the compiler takes your program, it translates into a series of instructions manipulating values on the registers. And along the way, the compiler assigns some number of registers to each thread. So let's say compiler ends up assigning R registers to each thread. Then a thread block therefore consumes accordingly many registers. And it has to be kept throughout the lifetime of each thread block, from the beginning to the end. And obviously, each streaming multiprocessor has only a fixed number of registers. Specifically, it is 32-bit, so 64,000 32-bit registers, both on earlier 2 generations, and I believe it is still the case in the latest generation, which is Ampere you are going to use. So the only point here is that the amount of registers you can have is physically limited, right? So one obvious limitation when you determine the size of a single thread block, which is BS here, is that R multiplied by BS cannot exceed 64,000. Well, so more precisely, this number of bits, right? So generally speaking, when you have a thread doing very complex calculations, taking so many registers to hold values, then you cannot make a thread block too large. So you can have only so many registers. Only so many threads within a single thread block, so that the total amount of space required for registers doesn't exceed this amount of space, right? So this is actually another absolute constraint that is imposed. And slightly different thing. So from the perspective of performance. So before getting into the specific question of what is the appropriate number of threads within a single thread block, so this is how parallelism within a single streaming multiprocessor actually looks. So its parallelism actually consists of 3 or 4 levels depending on how you count. So in the bottom level, you have a CUDA thread. So a single CUDA thread basically does not have any parallelism. So it sequentially executes one instruction at a time, right? And actually, the next level is something called warp. So which I have never talked about in the slide, but actually it's pretty important concept. So I'll come to this later. And yet another level above this warp is thread block, which I have been talking about so many times. And actually each streaming multiprocessor physical core can execute multiple thread blocks at the same time. So you can actually think of a single streaming multiprocessor having 4 levels of parallel. So this is a single CUDA thread. And actually a warp is a group of 32 CUDA threads. So a group of 32 CUDA threads makes something called a warp in NVIDIA terminology. So in other words, these 32, not necessarily in the other words. So I'll get to this later, but basically these 32 threads always execute exactly at the same time. And in the next level, thread blocks. So a thread block is actually a group of BS divided by 32 fractions rounded up number of warps. So this number of warps makes a thread block. So for example, when you say, okay, so you want to have 128 threads in each thread block. From the hardware's perspective, it is 4 warps. So a single warp is 32 CUDA threads. So 128 CUDA threads is 4 warps from the hardware's perspective. So what is the significance of this warp? I'll come to this shortly, but for now, just take my word. And there are multiple thread blocks executing simultaneously on a single streaming multiprocessor, which is illustrated like this in the entire figure. So in this figure, this is a single CUDA thread. 32 CUDA threads makes a warp. Some number of warps makes a thread block. And single streaming multiprocessor is able to execute multiple thread blocks at a time. So this is what is exactly happening in GPU. And okay, so why this work is significant from the programmer's perspective? So it has actually a huge performance implication. So like I said, a single work is a group of 32 threads. Having a consecutive thread IDs. So when you launch, for example, 128 threads in a single thread block, it gets number from 0 to 127. And the first 32 threads, 0 to 31, constitutes a single work. And the next 32 threads from 32 to 63 makes another work, something like that, something as simple as this. And from the performance perspective, what is significant is this second unit. So those 32 threads within a single work share an instruction pointer. So it never happens that in a single cycle, some threads within a work execute this instruction, and other threads within the same work execute another instruction. This never happens. So 32 threads need to execute exactly the same instruction in a single cycle, except that some threads within a work do not do anything. Well, it is actually very necessary in some occasions. So you don't want to execute this instruction by all these 32 instructions. So when these circumstances arises, what you do is, okay, in this cycle, only 10 threads do this instruction, and the other 22 threads do not do anything. So this is the only thing you can do. So again, so it is not possible that, for example, these 10 threads execute this instruction A, while the other 22 threads execute another instruction B at the same cycle. It never happens. It is not possible. So in a way, it is much like SIMD instruction you have on CPU. So SIMD instruction, I likely mentioned in the introduction. It is a single instruction that is able to do many operations with a single instruction. So to be more specific, the same operation like multiplication or addition on a number of elements with a single instruction. So it is very similar to work in the sense that you can do only the same thing, exactly the same thing with a single instruction. So GPU is in a way much like CPU in the sense that, okay, all threads within a single work have to do the same instruction in a single cycle. Okay. So what are the important performance implications of this work structure of GPU? So one implication is that, so there's really a point in making thread block size less than 32, or not a multiple of 32 for that matter. So for example, when you have only 4 threads within a single block, what actually happens is that you still have a single work, but 28 threads are simply wasted all the time. So you'd better have 32 threads within a single thread block at least. But likewise, it is rarely a point. There's rarely a point in, for example, having 40 threads in a single block. So in that case, you'd rather have 64 threads within a single thread block. So this is one implication. So the other implication is that, okay, so you want to let all these 32 threads do exactly the same thing, almost at almost every single site. So like I said, well, actually, it is not possible that, okay, some threads execute instruction A and other threads execute instruction B in a single cycle. But what if you, for example, write a program having a if expression? So depending on the condition, that in turn depends on which thread you are. And you have then statement and else statement doing different things. So what happens on GPU when you write something like this is, so first all threads execute the then statement, but threads that are supposed to execute else branch do not do anything while these other threads are doing the then statement. And only after everybody finishes then branch, the remaining threads start executing else branch. So like I said repeatedly, so it never happens that, for example, some thread executing then branch, while at the same time the other threads are executing else branch. It never happens. So when you have a work, you want to make sure that all these threads execute the same thing for the performance sake. So this is something called so avoiding warp divergence. So warp divergence means that, so some threads are doing something while other threads in the same warp are doing something else. This is something called warp divergence. And the execution time is simply stretched when you have warp divergence. For example, when you have 32 threads, each doing completely different things, then it takes 32 times more time than otherwise. So than the case in which everybody is doing the same thing. So just avoid warp divergence. This is one important performance consideration when you do CUDA program. And so here comes the original question. So what is the appropriate way to choose the number of threads within a single thread block? No. So this slide is not about this. So okay, but still so it's still about a similar topic. So okay, so this is another important thing you want to remember when you reason about the performance of your GPU programs. So which is, so how many thread blocks execute simultaneously on each streaming multiprocessor? Because so when you have an idea about, so how many thread blocks can actually execute simultaneously on each streaming multiprocessor, then you simply multiply this number by the number of threads you have in each thread block to get the number of threads simultaneously executing on a single streaming multiprocessor, which is a good approximation of the parallelism you have on each streaming multiprocessor. So it is actually determined by the resource constraints of streaming multiprocessor. So let's say you are executing n thread blocks. Then you need to have this number of registers while these n thread blocks are simultaneously executing, which is R, which is the number of registers each thread consumes, multiplied by BS, which is the number of thread blocks in each thread block. But multiplied by n, which is the number of simultaneously running thread blocks. So in order to execute this so many number of thread blocks, streaming multiprocessor has this number of registers alive while they are executing, right? And this number must be equal or less than the number of registers per streaming multiprocessor. This is actually the constraint that is imposed by the GPU on the number of simultaneously running thread blocks on each streaming multiprocessor. To get better performance, you want to actually increase this number, so BS multiplied by n, which basically represents how many things are going on in parallel, right? So to choose block size, you wanna sort of optimize this BS multiplied by n, given this constraint. So another constraint similar to registers is this. So let's say you allocate S bytes of shared memory to a single thread block. So S multiplied by n, the number of thread blocks simultaneously running, must not exceed the shared memory per streaming multiprocessor. So this is another constraint imposed on the number of simultaneously running thread blocks. So again, you want to choose S and BS. Of course, depending on what you want to do with your program, there are some other constraints you need to have. But all in all, you want to optimize this number within this constraint. So this is what you are actually you can do to optimize your the performance of your CUDA program. And as a matter of fact, so there is a simple formula you can use to calculate how much of the shared streaming multiprocessor resources your CUDA program can utilize. So there is something called CUDA occupancy calculator. You can simply Google it. But so this is duplicated, but it's not that it is not useful. But so this is actually a simple Excel file to which you can input the number of so the number of thread blocks the number of threads per block and the number of registers per thread and the size of the shared memory you want to allocate to each thread blocks. Then it calculates how much of the streaming multiprocessor resources this program is able to utilize. So you can have the approximated view of parallelism you have in shared streaming multiprocessor. So I come to these topics slightly in more depth in the next week, and I think it's time to finish for today. So before we finish, maybe I got another question. The next for so I guess you are talking about the OpenP exercise. So I guess